All right, mutual induction, a very important concept. We'll see that it has engineering and technology applications that are really important to how electricity is used in our society, modern day society. But first, let's unpack what's going on here, and it can get confusing because now we have two coils. We don't have a inductive constant L, we're replacing it with an M. We have to kind of bounce back and forth between what's going on with these coils. I know. This is going to take a little bit of time to absorb, so let's kind of do it step by step. The first thing that we want to do is simply take your page, and the first thing to annotate is only. Don't go putting in more annotations than just the blue, the B1. So we are going to focus on coil, we are going to focus on coil 1 only for the time being, okay? Coil 1 has a battery, right? So coil 1 is powered. It has a battery that begins to make current I1. Well, current I1 flows in the direction given by the battery, and it is going to make B field B1. So let's practice our Bio's Savart Law, IDL, right? Here's our IDL, tangent to the solenoid. Do an IDL, cross R hat into the center of the solenoid. Hopefully you're now pointing your thumb to the left and are comfortable with the B field that now gets generated to the left. Well, that B field then extends in space, even the space that is seen out here by coil 2. Okay, so now let's go over and begin to think about what's going on in coil 2. So no equations yet, don't worry about the rest of the notes. Coil 2. Coil 2 does not have a battery, so notice there's no battery on your blank page of notes. I have put in an induced EMF voltage symbol here, but it is not a battery. So hopefully, with what we've done with Faraday's law and Lenz's law, we can see that when nature presents coil 2, right, with the blue B field going to the left, Faraday's law and induced effects are going to kick in and make induced current to make induced B field to the right. So let's pause for a moment here and just convince ourselves that the current will be flowing in the direction shown, again, based on Savart Law, IDL cross R hat. So let the IDL run up the page, right hand, IDL cross R hat into the middle of solenoid 2, and hopefully your thumb is pointing to your right. And if you are having any difficulty with this, please make sure when we get back together in class, you sort that out with me so that your basic cross product IDL cross R hats are going in the right direction. So that's the basic premise in terms of what nature is presenting to these two coils. Well, let's see how this fits in then with our equations. So we know that magnetic flux through a single coil in general, right, is directly proportional to the current because it's the current that makes the B field in the coil. Well, now the magnetic flux that is making B field in coil 1 is the blue B field, right? So it's actually current 1 that is generating the flux in coil 2. So when we did self-inductance, one coil, we said, okay, that proportionality becomes an equality by putting in our proportionality constant. Now we're going to do the same thing, same concept, but introduce our mutual inductance constant, capital M, and we'll see that it's kind of an action-reaction type of pair situation where that M doesn't need a subscript for coil 1 versus coil 2. It is mutual. That's why it's the mutual inductance constant to the coils. So all we've done is algebra to get our expression for what the mutual inductance constant is based on our proportionality and then our proportionality constant. Well, Lenz's law and induced EMF still applies because we established that over here just looking at what nature would present to these two coils. And our induced EMF over here is going to be primarily generated, right, by the voltage in 1. So di dt, di1 dt is making B field 1, which is producing the current in, producing the flux, in coil 2, which is making induced current 2. Well, technically, right, we have to remember that coil 1 has self-inductance itself. It does. So the total voltage that is seen in coil 2 is actually what coil 1 is doing to generate anything. So this is our primary effect, right? So this is our primary term, and the secondary term in coil 2 will be based on the self-inductance and the fact that coil 2 is going to try to shut down its own effect. So you can see there's a can of worms that's kind of opened up in terms of, well, when one changes the other changes the other, and it bounces back and forth. We will never go past a first and second order effect. So here is our first order effect on coil 2, our second order effect on coil 2. Now let's take a look at first and second order effects on coil 1. In coil 1, we have a primary source of current, the battery, right? So our coil 1 has a battery, so we have that source. We have a primary effect on coil 1, which is going to be the self-inductance that coil 1 generates due to the fact that it's a coil, and Lenz's law applies to that coil. And then we have a secondary effect in coil 1 that is when the B field in coil 2 becomes present, it bounces back and affects coil 1. So, source, primary effect, secondary effect for the blue coil, our primary coil. The second coil, our secondary coil, the primary effect, right, we don't have a source, so we only have the primary effect is the time rate of change of the current in 1 making the B field that coil 2 sees, and then the secondary effect is the fact that there is self-inductance in coil 2 itself. So I do realize there's a lot going on here, and anytime we're introducing first order effects, second order effects, two coils, I realize it can get to be a little daunting. So our next lesson, next page of notes, is going to have a numerical example to look at, and we'll have to get more comfortable with this as we see more examples.